Let's get this started. Hello and welcome tonight to the talk with Rainer Grimm about concurrency patterns. Rainer Grimm, really honored to have you tonight as a guest and sponsor. So please take it away, speak about concurrency patterns with us.
Thanks, Jens, and let me start. I want to talk today about concurrency patterns. I'm a big fan of concurrency. Why? Because this is the challenging, this is the fun stuff. So, let's start. First of all, a few words about pattern, only a few words, I promise. And then we dive directly into the concurrency part. First of all, what's a pattern? This definition goes back to Christopher Alexander, who was an architect, but not a software architect, a building architect. Each pattern is a three-part rule which expresses a relation between a certain context, a problem, and a solution. I make it short. Okay, we have essentially three types of patterns. We have architectural patterns, which describe the entire architecture, the fundamental structure of the system. We have design patterns, which you may know from the design patterns book, for example. They describe the interplay of the components out of which the architecture is built, and they focus on the subsystem. You see, the architectural pattern focus on the entire system, essentially. And then we have then finally idioms, which are architecture or design pattern in a specific programming language. And what I do today is I talk concurrency about design patterns and architectural patterns. Each pattern has a structure. I will not bore you. This is all what you should know. And this is the structure. I think this is the Gang of Four structure, but the POSA structure is pretty similar. So each pattern has a name, has an alternative name, a summary, motivation, context, examples. This is how it's described. Okay, now let me jump into the interesting parts. First of all, I use, or my source of patterns consists of three books. First of all, Pattern-Oriented Software Architecture, Volume 2 and 4, and then Concurrent Programming in Java from Douglas, Dougley is only his name. By the way, this is a book which was written by people working for Siemens in Germany. Pattern-Oriented Software Architecture. In short, I always say only POSA. Okay. Okay, let's start with patterns or design patterns, and then finally let's talk more about the architecture. There are two meta rules. Two meta rules you should be, which you should follow when you do something concurrently. And here are the two meta rules. Be as constant as possible, work as local as possible. And therefore, I first talk about being local, or meaning don't share, and here being constant, meaning dealing with rotation. Let me put it differently. What you don't want to have is a data race. A data race is concurrent writing and reading of shared state or shared data. This is what you don't want to have. This is by definition undefined behavior. And it is pretty easy to get no data race, because requirements for data race is shared mutable state. When you only get rid of one of these, both, there could not be a data race, because when you don't share, there is no data race, and when it's constant, it cannot be mutated. And therefore, I start now with dealing with sharing and dealing with rotation. So, first rule, copied value. It sounds extremely straightforward, but this is straightforward. There's no need to synchronize when a thread takes its argument by copy and not by reference. You see, by copy means each thread has its own data. Each thread works locally on its data. Therefore, you cannot have data races. Let me show you something. By the way, I have always examples involved. When you have the slides, you can try them out. I have 3 threads. These are C++20 threads, G-thread. All of them take a Boolean shared, one by copy, one by ref, one by const ref. And then you see I change shared to true. And because these threads use this shared here, this is a data race when you take when this function takes this shared by reference, you see, such as here, such as here. You also see when you look at this output here, that both the function by reference and the function by const ref modify shared to true. Now you have concurrent writing and reading. Here you read, here you write. And maybe you don't believe me, there's an extreme good tool which you should always use when you do concurrent stuff. And this tool is integrated in GCC Clang, and therefore I can use it here. Use the sanitizer. Sanitize equals thread. And now you see an ugly output. And sanitizer detects a data race. And let me see if I can see more. Line 16. Line 16, line 16, line 60, this line here. And you see, this is the B. So you can also visualize this data race using thread sanitizer. I strongly suggest, this is not a pattern, this is more best practice. Whenever you do something regarding concurrency, always use thread sanitizer. Thread sanitizer finds with high probability, extremely high probability, the easy data races. What do I mean by easy? Data race on single memory locations, such as a bool here. Okay, let's go further. So this was commit value. There's another way to don't share. Use thread-specific storage. Typical use cases of thread-specific storage are, for example, you have a single-threaded program and you want to make this multi-threading. You want to port it to multi-threading. What people often do in the first case is they just make their shared state thread local. Therefore, each thread gets its own copy of this shared state. What is also typical use case of thread-specific storage is a thread local logger. You want to know which thread created what. Therefore, to make the logger thread local. Let me show you an example. I use this time Wendbox, a different online compiler. What I want to do is the following. I want to sum up. Where is it? 100 million numbers randomly created, you see, between 1 and 10, sorry. And I have 4 threads. Therefore, what should I do? Of course, I have 4 cores. What should I do? I create 4 threads. So I have a thread T1, T2, T3. Each one performs the function sum up. Here's the function sum up. It takes an atomic unsigned long to store the value of this summation. It takes the vector of arbitrary values and says from begin to end, use this vector here. And now I go through this vector, you see, begin, end. This is my vector. And I sum up all values. And I do it on TMP sum. And here's the key point. TMP sum is thread local, meaning each thread has its own copy of TMP sum. Therefore, there is no sharing, therefore, there is no data race. And then when I'm done with this calculation of a fourth of this vector, I just add it together using sum, fetch, or add, and this is fine because sum is a, let me see it here, let me show it here, sum is a atomic, here you have it. And this is, how should I say, a thread-safe way to sum up in big vector, and by making 4 pieces out of it, and each thread uses one part of it, 1/4 of it. Okay. And here you see that this thread gets its variable by reference. Let's jump back. I don't have an example here, but this is most of the time the easiest way to do it. Just make a future promise pair. This is .async, which performs this function here, this lambda function. This .async does not return a value, it returns a handle to the value. And now you can use get to draw the value out of this. This is called promise. Once more, we have a pair out of a promise and a future. The promise promises to produce a value, which the future picks up in the future by saying .get. And the nice point about this construct is there are 2 extremely interesting properties. First of all, this channel between the promise and the future is safe by design.
Rainer?
Yeah, yeah.
There's a little technical issue I would like to address quickly with you. Your mouse pointer basically leaves copies everywhere on screen when you point.
Yeah, then
can you
let me just jump a little bit forward back? Is it now? No, it's still there. I can see the background.
Gone.
Now it's gone. Let me put it here, and then I will not use my mouse pointers. Therefore, you have to exactly.
Yeah, that's probably the solution. Not to.
I will observe myself in the second window, then I see when I have an issue.
Okay.
Okay, here we are. Future promise pair. Okay. Once more, the promise is the sender. It produces something. It sets something in the channel, which the future, the receiver. Here, this should be fine. The future, the receiver gets or draws out of the channel. And there are 2 interesting points. First of all, the channel is protected. No one can see the action which is happening in the channel. And second, the channel is flexible, extremely flexible, meaning the promise and the future can be different threads. So once more, there is no data sharing here. This is how also we can solve the issue of data sharing. So this was it about sharing. Now we deal with the next thing, which means mutation. Mutation means we have different kinds of locking. Let me directly jump into this stuff. First of all, we have scoped locking. Scoped locking is essentially the Ray idiom applied to locking. And what's the idea? The idea of Ray is the following. You acquire in the constructor the mutex, meaning you lock it, and you release it in the destructor. So you make a guard object which takes care of locking and unlocking the underlying mutex. Then you scope the lifetime of this thing. And then finally, the C++ runtime is responsible for invoking the structure and releasing the source, because this object, this guard object, is a local, a scoped object. And we have scoped locking in various flavors. We have lock guard unique lock since 11. Oh, now I have to be extremely. Since 17, we have scope locked. I think since 14, we have shared lock. I'm not 100% sure about shared lock, but pretty sure. And now let me show you an example. Here it seems to work. Okay, this is good because this would be terrible if I cannot show what I wanted to say. Okay, we have here in scope lock, you see, this is, by the way, modeled after lockup. This takes the mutex by reference. It locks the mutex in the constructor. It unlocks it in the destructor. And this is my, I say scope lock, you can also say my guard. And now I use it. I have here mutex, which is now, the scope lock is responsible for it. And therefore you see here, the mutex is locked because I displayed the address of the mutex, and here the same address, therefore the mutex is unlocked, meaning when is the mutex 1 unlocked? When scope lock 1 goes out of scope, and this is exactly in line 47, and therefore this is the last line we see. Once more, this is RAII, Resource Acquisitions Initialization. Here I have a mutex in a local scope. Therefore, we see here before local scope, after local scope, and here lock the mutex, release the mutex. And this pattern this idiom would not be so good if it would not deal with exceptions. Have a look. I throw here intentionally an exception, a beta lock. But this is not an issue, because here before try catch block, after try catch block, you see, and here exactly 9:39, the scope lock 3 goes out of scope, therefore mutex 1 is unlocked. So this happens in the good case, such as here, but also in the bad case, meaning an exception occurred. And this is the benefit of RAI. You have, which is extremely nice, deterministic destruction behavior. Exactly here the destructor is called. And you see here, even before you display the exception, stood back unlock. You see, release the mutex. This is RAI. In this case, a special way of using it, meaning scope lock. Let's jump back. Then we have strategized locking. The idea of strategized locking is another idea. The idea is the following. Assume you have some component which you want to use single-threaded, multi-threading in different cases. And this is a library. And now, depending on the way you use it, you want to apply different locking strategies. And what, of course, would work to always lock, but this makes no sense when you are in a single-threaded environment. So what you do is you want to apply exclusive locking, shared locking, or no locking, depending on how you use your stuff. And therefore, you configure your locking strategy. And essentially, you can do it in both ways. I will show you both ways. You can do it at runtime, or you can do it at compile time. Essentially, strategized locking is the strategy pattern applied to locking. When you do it at runtime, what's the advantages? You can even change it at runtime. You can go from locking to no locking or something else. What are disadvantages? Okay, it's a little bit more expensive. You need a point interaction. When you do it at compile time, it's essentially for free. You get flatter object hierarchies. But, templates are a little bit known for that, but I can deal with this fact when I show you the example. You get maybe not pretty error messages. Let me show you strategized locking. This is at runtime. So I have here a class lock, and here I have a strategized locking. And this strategized locking gets in its constructor a lock. And this lock has to fulfill this interface. Lock, unlock, you see, pure virtual. an abstract base class. Now I have different classes deriving from lock. I have no lock, which uses internally the null object mutex. And you see, this is a mutex which does nothing. Then I have here an exclusive lock, which uses a std mutex. And then I have here a shared lock, which uses a shared mutex. And by the way, being const is a virtue, you see? But because I lock, for example, here, my mutex and unlock here, it cannot be const. And therefore, I made it mutable, therefore I can lock it, or I can modify it in a const member function such as this one and that one. This is a nice use case for mutable. Okay, and then I just put it together. I have strategized locking with no lock. Then I use the exclusive locking. So my strategized locking has underhood this exclusive locking. And here I have my shared locking. And here you see the interleaving of lock and unlock calls. This lock here lives until line 81. Therefore, we see here unlock. And here you see it more concise, shared lock, lock, unlock. And here I essentially use three different locking strategies. The no-op locking strategy, the exclusive lock, here we are, sorry, exclusive locking strategy, and finally the shared locking strategy. Okay, a little bit, let me modify it a little bit, and then we can do it at compile time. And instead of an interface, I define a concept, basic lockable, meaning I want to pair my strategized locking on a thing which supports basic lockable, and this is what it should do. It should support lock and unlock. And this is essentially all. This is almost the same such as before. The big difference is, here we are. The lock is a template argument. This is all. But once more, this is a compile time decision. Therefore, there's no runtime penalty. But also, you cannot change it at runtime. This is also the strategy pattern blind. You can also say, you say here, you hear here more often the policy. You apply different policies. But essentially, it's a strategy pattern from the Gang of 4 book. Okay, let me jump back. Next pattern, thread safe interface. Let me go to the, thread safe interface. The thread safe interface extends the critical region to an object. Okay. Why? There's an anti-pattern. I will show it to you in a few seconds. And this is the following. You want to use an object in a threading environment, and what you do in each member function you call first lock. This has two extremely bad consequences. First of all, your performance will go down because you synchronize maybe too much. And second, you have a high probability of deadlocks. Let me show you what I mean. This is a class critical. It has a method 1, which first calls lockguard mute. And then it has a method 2, which also calls lockguard mute. And now let's see what's happening. By the way, I should give this lockguard a name. Sorry, there's a small error here. But see what's happening. You lock here, then you want to lock here once more. Therefore, you have here deadlock. Assume that mutex is not recursive. Here, it's not mutex. Therefore, it's exactly speaking undefined behavior, but you can assume deadlock. Therefore, you have here this lock cannot be successful, but you will not come back to unlock it because this does not work. Therefore, this is a typical receipt for deadlock. And here the thread safe interface pattern kicks in. And this is the idea. All interface member functions public should use a lock. All implementation member functions, such as protected and private, must not use a lock. And now an interface member function can only call implementation member functions. And when you follow this pattern, you will not get a deadlock. But of course, this costs a little bit because you have always a kind of interaction going from interface to implementation member functions. And you have to carefully think when you have static members or virtual member functions, because then it becomes more complicated. But anyway, here's the idea. Let me show it to you. Let me have interface 1, which calls the implementation function 1, and I have interface 2, which calls 2, 3, 1. And these are the implementation functions. They are invoked without synchronization, of course, because you already synchronized here. And when you now invoke it, such as here, thread T1, it performs this lambda, which takes this critical data, then calls interface 1 of it. This thread 2 calls 2 and 1, and this one, the main function, calls 1 and 2. And here you see what's happening. Let's see if we can observe what's happening. By the way, these are the thread IDs. This helps you a lot to see which thread is active. This means, first of all, this function is invoked. Interface 1 calls implementation 1. Then we have 1, 2, 3 with the same thread. 1, 2, 3, and 1. This means the main function is invoked. First, interface 1, you see. Interface 1 calls implementation 1, 2, 3, 1, 2, 3. And finally, once more, interface 1, which calls only implementation 1, and so on. So you can see from this output how the interleaving of thread went. And this is the thread safe interface. Okay, and now to the last classical pattern, and then we go in the direction of architecture. Guarded suspension. What is the idea of guarded suspension? The idea is that your object has a lock and a condition. And the condition has to be fulfilled before a thread can be active on the object. This means the calling thread will put itself to sleep if the condition is not met. I'll show you an example in a few seconds. The calling thread uses a lock when it checks its condition, and the lock protects the calling thread from a data race or deadlock. Okay, let's make it more concrete. This is not concrete. I will show it to you here, 2 examples. We can do guarded suspension in many ways. Once more, the idea is that you have an object which is protected by a mutex, and you want to work on this object, and to invoke something on the object, you have to check the condition variable. So we can do this in different ways. The waiting thread is notified about the state change. Remember, you want to call something on an object. You cannot do it. And then when it's done, you may be notified. So we can do both. The waiting thread is notified about the state change or ask for the state change. So I call this push or pull principle. We only have the push principle. This means you want to do something on an object. The guy who used the object before does not need it anymore. Therefore, you can use a condition variable, a future promise pair, atomic, sledge, berries, or semaphores to make this happen. These cases here, starting with atomics, are only possible in 20. I will show you an example with I think with a ledge. The pull principle we don't support it natively in C++. There are more variations how you can implement guarded suspension. You can wait with a time limit. This can be done, for example, with a condition variable or future promise pair. And finally, you can send your notification not only to one thread, but to many threads. And this can be done with shared futures, condition wrap, atomic ledgers, and you see. So you see there are many, many variations to do it. And before I do now anything, I will not show you an example to condition variables. You can be really, really happy because condition variables are really, really hard and really, really complicated. I only show you a future promise example and I show you a ledge example. This is based on 11, this is based on 20. Here's a small workflow based on a future and a shared future. And this is my idea. I use a promise. Sorry, it looks strange, but when a promise sends a notification, it returns void. Then I draw the future out of this promise. You see, this is my promise, this is the future. And now I have 4 workers. I have Herb, I have Scott, and I have Bjarne. And what they do is the following. They perform this function object. They get, you see how prepared. This is the promise by, it's moved inside and the future is copied. Why? Because the future is a shared future. So once more, I have 3 threads, Herb, Scott, and Bjarne. Each gets in promise and in shared future. And it uses the shared future to be notified by the boss when they can start to work. And they use the promise to notify the boss that they are ready with preparation. Let me show it here. This is what my workers are doing. They get the promise by R-value reference and the future by copy. They work for an arbitrary time duration, you see, between half and 2 seconds. And when they are done with their preparation, they say prepare set value. This is the notification. Here they signal to their boss, I'm done, prepare my work. And the boss is waiting here. Wait for Herb, wait for Scott, wait for Bjarne. So the boss is waiting until here, until the boss gets notification of all his workers. Then he says, the worker says, work prepared after such amount of milliseconds. When all threads or workers send their notification, the boss can continue, and now the boss sends its notification set value, which goes to all futures, and these futures are shared. Therefore, all these futures wait until the boss sends its notification. And then they are, what should I say? They are done with their work. So do you see, this is a 2-time synchronization. First, the worker prepared their work. They notify the boss, hey, we are done. The boss continues when all 3 send their notification, and then the boss by himself sends the notification. You can start your work. You see, prepare your work, start your work. Okay, this was honestly a pretty simple workflow, and I'm happy that I didn't have to explain it to you using condition variables, because here I strongly prefer futures and shared futures and promises also. And here's the same workflow upgraded to C++ 20. And here I have a ledge, 2 ledges, one for the workers, one for the boss. And this ledge, let me explain it here. This is the worker. This is the first ledge. You see, work down. And this means exactly here, when the thread performs this line, this counter is decreased by 1. And when this counter becomes 0, the worker continues until here he waits. And this go home ledge has a value of 1. Why? Because this is the ledge which is, let me say, signaled by the boss saying countdown. So let me put it once more differently. This is the main program. I have workers, I have G thread, also 20 thread. They perform the work help, Scott, and Bjarne. And then the boss waits also. The boss waits here until this counter becomes 0. And this counter becomes 0 when all 3 threads decrease the counter by 1, because the initial number is 3 and we have 3 threads. And when this becomes 0, this call is unblocked, or this wait step is done. And then on the contrary, the boss says go home, which decreases this counter from 1 to 0, and therefore the worker can continue here. And this is how this workflow goes. And this is a ledge, which is a nice abstraction in C++20. And you see, this is pretty easy to digest. Okay, let me continue. Now I come to the not so easy to digest stuff. Even my exams are pretty straightforward, but this is more challenging. Now I show you two architectural pattern. I think the monitor object is natively supported in Java, but I implemented it in C++, and I show you the active object. The active object is a nice pattern. The active object separates method execution from method invocation. This means each object owns its own thread. When a client wants to invoke something on a server, this method invocation goes to a so-called activation list, and a scheduler triggers the method execution which is stored in this activation list. I will show it to you with an example, so bear with me. It's a little bit more complicated. So essentially we have, you see here, 6 participants. First of all, the client. The client wants that some method is performed on an active object. The active object runs in a different thread. So we have essentially 2 things. We have a client or clients and servers. In between is an activation list on which the prepared jobs are stored. So the proxy the client calls the proxy, which triggers a member function on the active object. This member function goes to the activation list, and this proxy goes back to the client. This proxy call also calls a method request, which has all which is required to invoke the method. The method is not invoked, it's just stored. It's stored on the activation list, and this activation list decouples the client from the active object thread. And in the active object, there's a scheduler which looks inside the activation list and decides which job should be executed next. In my simple example, I just use the next one, but you can do here a lot of more sophisticated stuff. There are 2 additional components. First of all, there's the servant. This is the guy who performs the job invoked by the client. This guy also supports the interface of the proxy. And finally, there's the future. The future represents the value. The future represents a handle to the job which is stored on the activation list, and which the client can use later to ask for the value, if there is a value. Okay. So let me explain it once more from the dynamic point of view. The client invokes the method on the proxy. The proxy creates a request and passes to the scheduler, and the scheduler enqueues the request on the activation list and returns this what you enqueue on the activation list. Think about it as a promise, and returns the future to the client if the request returns something. Now we have some job description which can be performed. Think about a promise which didn't immediately start. It's essentially, I use the package task. So the member function execution, what is happening now? The scheduler determines which request becomes runnable, which one should run next. It removes the request from the activation list and dispatches it to the servant who should perform the job. And now what's happened in the completion step? The servant stores this result in the future, or so in the promise, which the future can use to pick it up. And then when the future has the value, of course, you can delete the promise. This is the workflow. And to make it simple, this is the client thread, and this is the server thread. And in between is the activation list. And you see the client asks the proxy creates a future, which becomes a request object, which is stored in the activation list. I hope you can see me. You can see my mouse. Sorry, here it is. It's in the activation list. Then the scheduler dequeues something from the activation list, performs it on the servant on the right, and it puts the result back. And the client can use the future to pick up the result. And now let me show you an example. Oh, first of all, advantages, disadvantages, and then let me show you an example. And here's an example. What is nice about this pattern is the following, extremely nice. The only thing which you have to synchronize is the activation list. This is extremely nice. This is the only stuff which must be thread safe. You have a clear separation between client and server. The job is done asynchronously. It is not done synchronously, not done immediately. Therefore, you have improved throughput. And the scheduler can take the jobs out of the activation list in different ways. So you can write a really sophisticated scheduler. What are disadvantages? Of course, there's a lot of interaction. Therefore, there's a performance penalty here when the jobs are too fine-grained. And of course, the system is pretty complicated to debug. When you see the structure, you can immediately assume to know what's happening, what went wrong, and so on and so on. Okay, now I'll show you an extremely simplified example, but honestly, even this is simplified, it's not simple. Here we are, active object. Now, this was the wrong button. What was happening? Full screen mode. I should jump. Here we are. Does it work? Now it works. Okay. I have a few clients here. So this is my job, and then I explain you what's happening. This is my active object. I have 1, 2, 3, 4, 5 clients which are performed in 5 different threads. Each client produces random number 1998, 23, 2011, 2014, and 2017 random numbers between 1 million and 1 billion. And what is my job? To decide if this random number is a prime or not. And here you can already see the result, to which I will come. So what is happening? First of all, we have the active object. Here's the active object. It has an extremely simple interface. It has a member function to enqueue and job. It has a function to schedule, to run the jobs from the activation list. And the activation list, you can see it here, is a deck of package tasks. Package task is a promise kind thing. And what this package task has is a function object, a callable. And this callable gets no arguments and returns a bool in an int. And the bool signals is this prime not, and the int is the number. And because this activation list must be protected, I have a mutex for protecting this activation list. And now let me show you my program. First of all, I invoke the functions getFutures with getActivation object and the number 1998. GetFutures is this function. It gets the active object and the numbers of primes, the numbers which are created. By the way, these are so far no prime numbers, these are just numbers. So here I have a vector of futures, bool int. Then I create here number primes, random numbers. And for each random number, I create a job, which I put on the activation list, you see, which is part of the active object. Let's see what enqueue task is doing. This is enqueue task. Here we are. Where's my enqueue task? Here we are, enqueue task. First of all, this is a function object which determines in its call operator if the number num is prime or not, you see. If it's not prime, if it's prime. It's just a simple function who determines if a number is prime. And here's the interesting part. This function is prime. This is the job which is part of this promise. And this prime stores the number it should decide if it's prime or not. Then out of this package task, I create my promise. You see, get future. Out of this future, I create out of this promise, once more, out of this promise, I create a future. Then I put this promise is prime. This promise, new job. I put it on the activation list, you see. And this is stuff I have to protect because this is done concurrently. And what I return is only the future, the handle to the result. So the job is on the activation list and I got back the future. And here is enqueue task, and you see it here, enqueue task. And here I push back the future. So here I have all futures, a vector of futures. And each future returns a pair, the bool signaling it's a prime or not. The int is the number. So then I unwrap the first future, the outermost future, and I got back a vector of futures, you see, get. And here, for convenience reasons, I put all the futures together. You see, I just move them in the first future. This makes it easier for me. And now the job starts. I say active object 1. Now this is the scheduler which says, now perform these jobs, these promises, or in this case, more specific, package task. Let's see what run is doing. Run calls Where's my run? Here's my run. Run calls this function run next task as long as there is a task. So what is run next task? Here it is. It uses a lock guard because now it acts on the activation list. It asks first if the activation list is empty, meaning all jobs are performed. If not, it draws the first package task out of the activation list. It pops it from the activation list, which is a deck, and here the promise runs. Now something is happening. Here the promise runs. And I do it until it's done. So when I'm here, all promises are performed. And now I reserve space for my future. And what I do now, I copy all the future results into my future vector of pair bool int. You see, this is a vector of pair bool int, where bool is signaling it's prime or not, and int is the number. And now I sort it. Why? Because when I sort this, I got first all which are non-prime, because false is smaller than true. And then I got the ones which are prime. And therefore, I search in this vector for the first occurrence for pay first, which is the indication prime, not prime, if it's true, meaning here the prime number starts. And this is what I display, you see? This is what I got back, an iterator, and then I return all from this iterator until its end. And this is what you can see here, by the way. I got 544 prime numbers, and here are the prime numbers. And I got 99,499 non-prime numbers. And here are they. This is from the begin until the true, until the point I got here. I should not say point, I should say iterator. Okay, this was once more. I have to say, this was a simple example. But of course, this is a challenging architecture. Okay, this was the active object. And this was the hardest part of my, or most complicated part of my talk. Now let me talk finally about another concurrent architecture pattern, monitor object. This is pretty similar to the active object, but there are two big differences. First of all, the client and the server run the same thread. The active object, the client and the server run different threads. Second, it's an extremely simple scheduler. It just takes the first job. So a monitor object synchronizes access to an object so that at most one member function can run at any point in time. Therefore, each object has a monitor log and a monitor condition. The monitor log guarantees that only one client can execute a member function of the object, and the monitor condition notifies the waiting clients, because the guys who cannot run have to wait. This is the, let's say this is a class diagram. This is a class diagram, you see? I have a monitor object which has a few synchronized methods, which are, by the way, based on the thread-safe interface, or should be implemented using the thread-safe interface. It has a monitor log, which log and unlock call, and it has a notify and wait thing. In this case, I use a condition variable. Okay, so these are the components. Monitor object supports member functions, which can run in the thread of the client. This member function has synchronized methods, and at most one member function can run at any time, and they should apply the thread-safe interface, which I explained before. Then this monitor object has a log, which guarantees exclusive access to the member functions. It's about synchronization. And it has also a monitor condition, in which the member function invocations are stored. They have to wait until this object is not used by any thread anymore. And when the current thread is done with this member function execution, this next thread is awoken. This is the idea. And this awakening mechanism is the job of the monitor condition. What are the advantages? Benefit, of course, is the synchronization is embodied in the monitor object. The client does not have to care. The member function is automatically stored and executed. And the monitor object is a simple scheduler. First comes, first served. What is not so good is there's only one way to perform the member functions. First comes, first served. And you use under the hood the thread safe interface. And here, of course, when you do it wrong, there's a chance of a deadlock. When one public member function calls another and both use a lock, you have an issue. And now, finally, let me show you the example. And here is the implementation of the monitor. You see, it has a lock in which it calls under the hood monitor mutex, locks this mutex. It has an unlock, which unlocks the mutex. It has a notify one, which uses a condition variable, you see it here, to send a notification. And it has a wait, which has an additional predicate to don't get a victim to spurious wake up and lost wake ups. This is a terrible thing. This is condition variables could be victims of spurious wake up and lost wake ups. And therefore, you have to use an additional predicate. And by the way, here I don't use type name or class. This is a concept from C++20. A predicate is essentially a function which returns a Boolean. And to use it, I have to use the header concepts. And now I derive from monitor my thread safe queue, because what I do is I have a queue which I want to make thread safe. Therefore, I derive from monitor my thread safe queue. I have a function for adding something to this queue, you see, type parameter t, and I have a function for getting something from this queue. And therefore, I say here log, which use this monitor function log. I push something on the queue, then I call unlock, and notify one, by the way, is thread safe. Therefore, I don't have to do here anything special. Second, I have the wait call. First, the wait checks if something is in the queue. When so it logs, it takes something out of the queue and it unlocks. And you see, this gives me a thread safe queue. And it only supports two member functions, one for adding something, one for getting something. Okay. And now I have this is my program, and then we are done with this concurrency pattern stuff. This is my thread safe queue. I have a function add lambda, a function get lambda. What add lambda is doing is the following. It adds something to the queue. It displays the value, it's thread ID. And this is, by the way, what you can see. And here, this is what added to the queue. You see 1, 1, 1, 3, 4, 5. The reason is pretty simple. Because, where is it? I cannot find it. I cannot find it. Damn. Anyway, save queue add. There. I let a dice run, and I create random numbers between 1 and 6. So add lambda, save queue add, save queue while. This is wait. I'm a bit irritated. Anyway, save queue. Okay, now I have it. Here I invoke the dice, you see. Here I invoke my dice. And this thread performs this function add lambda. So this is what is performed, and this is the random number. This is what my add lambda needs, and this is what my add lambda gets here. and therefore we get here the numbers from 1 to 6, depending how this dice goes. And in the other part, this is my my get lambda member function, which runs also on its own thread. And here, because I do threading using C++11, I have to join my threads explicitly. And once more, I have 10 threads creating random numbers, and here you see the thread IDs. Therefore, you can see the numbers are different. Therefore, 10 different threads are running. Honestly, 20, because I forgot to mention this one, which I created here. Okay. This was the monitor object, and the idea is essentially you have an object which has both a lock-unlock facility and a notify wait capability. Okay, let me jump back because I'm done. So these were the patterns I presented. These patterns are more fine-grained. They deal with the two key concerns of concurrency, sharing and mutation. Once more, when you can get rid of one of them, you are thread safe by design because no data can happen. And these are the two patterns which deal with the architecture, and this is the active object and the monitor object. Okay, now I shut my mouse, and I hope, okay, it's just in time. And do you have a question? Hi, Jens.
Yes. Hello, Rainer. Nice talk. So let's start with the questions. Speaking about STD Future, what do you think about proposals like N number that proposes a continuation pattern for?
I know what you mean. I know what you mean.
Okay.
This is a great idea. And honestly, this is the future of the futures. We probably should have it with C++20, but due to discussion around executors, it is delayed by a few years. And we don't have it with C++23, maybe with 26. I'm a big fan because now you can combine futures. We should interfaces such as .then, when all, when any. Now you can build big workflows out of existing futures. But this is the future of the futures.
Indeed. What do you think about the need of lock if a data is only read in another thread concurrently, whereas only one thread is writing to it? Is locking still required or not?
When you have concurrent writing and reading, you must protect. This is extremely simple.
Yeah.
You can optimize it a little bit. You can use a shared lock, and this means at one point in time, arbitrary number of threads can read, but only one can write. So you can weight them in different ways. But once more, you have to protect. Either exclusively or, as I mentioned it, shared, and then Stati, please read the write logs or read it on my blog posts to get the details.
So when talking about architecture, I just saw that your member class had a public lock and unlock function. And I wondered, why are your implementations, they're not like using scope level locks like lockguard? Because if the key if the key you are using there, you're making thread safe, if that key throws, then
which example exactly? I'm not sure, because all of
on the monitor object, where you make the key thread safe.
No, I see. Let me go back.
And you had
if I have an issue here. Okay, I see your point. Now I have it.
And in between you called something in key right there.
Let me think about it. I see your point.
So scroll down a little bit, go to add.
Okay, when you would throw here an exception, you would not unlock it here. You're right. this could be improved by using a scoped guard, which is essentially a guard which takes care of underlying mutex. Let me think about it. Good point. Let me think about it.
Okay. Is SC promise and future pair a useful use case pattern for a controller thread to start some threads one by one in order and wait until each finish its initialization work so that next thread
Honestly,
is created?
I'm not totally sure if I can answer your question exactly, but let me just say a few words. First of all, a promise future one is a one-time thing. So you can a promise can only say once a notification, and then you have to establish this pair once more. This is really a pity with C++11 because for a ping pong game, so forwards backwards, you need a condition variable. But here's my point. With C++20, you can even synchronize on atomic flag, or you can even use ledges, barriers, or you can use semaphores. All of them are way faster than condition variables and way easier to use. But when you have a one-time synchronization in 11, I strongly suggest that you use a promise future pair. Condition variables are terribly complicated. I have, by the way, written a post about it. If you don't believe me, let me just show it to you. And this is, for a reason, one of my most heavily used read posts. You see, be aware of the types of condition variables. More than 300,000 times. You see, they have many issues. I hope this answered your question.
I think it did. Why do we need scope block implementation if C++ supports lock guard? I think that's like the beginning of your talk. I think you just show like how this is implemented, how it works, so that people understand.
That is a good question. We got the scope lock with C++17, the lock guard with 11. The main difference is the following. A lock guard can only get one mutex. A scope lock can get an arbitrary number of lockable things. And the issue of the scope lock is it guarantees that they are locked in an atomic step. This is a main issue. And the scope lock supports it. And when you study scope lock on CPU reference, you see it has to take at least one argument and an arbitrary number of arguments. So at least one, let me put it this way. And once more, the key point is locking lockable things in an atomic step is a big challenge, and the scope lock provides this.
And one of the reasons why it exists both is that we could not go back and change the lock guard class to do that because there's problems with ABI stability.
This may be a reason. I never thought about it, but
I know that.
They are both extremely simple. They don't support an interface. They only can lock and unlock.
They couldn't add on lock guard because lock guard was like the API was closed and they couldn't implement it. So like, let's put that functionality in a different object.
And so the scope lock is also extremely simple. It can only lock an arbitrary number of lockable things. I say lockable things because it's essentially a concept.
Okay. What exactly does concurrency and parallelism mean? Could you show like an example of the same?
Concurrency means this is essentially a question of definition. I'm not sure if there's at least 5 different definitions. What I always do when I write a book is write a definition I use in my book. Therefore, you at least know what my understanding of this term is. Parallelism means when something really runs in parallel. You have 4 cores and it runs in parallel. Concurrency means when something runs at the same time. This can still interleave. You can simulate concurrency with one CPU because the scheduler always lets something different run. And this this is my definition or difference between concurrency and parallelism. Many other people also have the same definition, but this is my definition. So parallelism means really doing something at the same time, and concurrency simulating parallelism.
So I think the best explanation I've heard so far was that concurrency is basketball and parallelism is track. So in concurrency, you have a lot of dependencies on other processes, and you communicate. And parallelism, it's more about sorting through a list of numbers with multiple threads. There's each thread has its own block of numbers, sorting it, and then there's later one big sort for the rest of the numbers.
I'm happy that you explained this picture to me, because so far I know this picture, but I couldn't understand it. Anyway.
Yeah, it's probably not accessible to everyone.
Okay.
So someone here, Peter von Niederhausen, says concurrency depending on data shared by all. Parallelism does not incur sharing. Yeah, that's also a good take. Let me see. We're not running out of questions so far. If you want to upvote questions, that also helps me choose. Just gonna drop those. I already did. And there's an architecture question. How about that? If you don't upvote things, then I just pick. So architecturally, do you prefer a single-threaded object with a channel to share data or thread-safe objects?
Oh, this is a complicated question. Honestly, I don't know. I strongly assume we don't have one solution which fits all. Yeah. And channels are extremely nice abstraction, extremely nice, in particular because they are protected. And thread-safe objects, let me put it differently. I assume that you have to think way more about thread-safe objects compared to shared data, compared to a channel, because a channel is crystal clear. You have two components and they are just connected with a thread-safe channel, whatever that means. But with thread-safe objects, you have to think about deadlocks. You have to think about if this is implemented in the right way. You have to think about, as we saw it before, should I use a mutex or should I put this mutex into a lock guard to be safe when an exception happens? I think thread-safe objects are a few steps more low level, and therefore I now would say I would prefer channels. But once more, there are so many different abstractions here. One is this future promising, and there's so many different abstractions.
Okay. Would you advocate for using mutex or recursive mutex by default? Why?
By default, always go for the simplest solution. This is the mutex, because it is probably the fastest one. And when you want to have recursive mutexes, honestly, I never used so far recursive mutexes. But when you need them, because you have to lock it 2 times and to unlock it 2 times, then this is your case. Let me add an additional remark. When you use a mutex from the same thread, a mutex, not recursive, a mutex from the same thread, recursively, this is undefined behavior, but you get this hyperpotentiality at deadlock. But it's undefined behavior.
Yeah, and when debating what is the best mutex, then one also has to bring in that under Windows, you may want to look into the binary sizes of the mutexes. Shared mutex is smaller than mutex under Windows, as far as I know, in the ABI. because
really, I did only a little bit of performance measurement. I was really astonished how slow shared mutexes are. But anyway.
Yeah. So, and of course, when you make that decision, what kind of mutex you want to use, you should measure. This
is a different point. This is a totally different point. And when you measure, I can say a lot how you should measure, but this is a different story.
Yeah, but I've just played around with so many things and measured via what's the website? Well, it's on my blog, and I was like astonished, like how really like you can see a difference in the same code with different compilers and or even the same compiler in a different version. So
yeah, this is exactly what I say. When you measure something, when you change anything in your environment, you have to measure once more. Anything. Different flags, different compiler, different hardware, do it once more. Different C++ standard, do it once more. And therefore, you should put your measuring functionality under version control.
So there was actually also a question on LinkedIn I should quickly bring on the screen. Someone, I think this was during the active object, is this how an asynchronous method invocation is implemented?
Is this a question or a remark? I don't see it.
I'm not sure about, but it's just something I thought I wanted to bring up to you. So I think that asynchronous invocations is probably one way to implement it, but I think it's more like this is more like one thing which you use for RPC. Am I right? Like active object, would you use that to implement an RPC call?
I'm not. You probably mean remote procedure call, but you can do it. Maybe there's also a network in between, but the essential point is you can make this bigger and bigger. It's asynchronous, and there's a lot of additional infrastructure you can do here and there. But the key idea is this activation list, and you have which has a thread-safe interface essentially. But you see, there are proxy. You can also create from an interface definition language a stub in the skeleton which you have to implement. So this goes direction of Corba. So there's a lot of additional stuff which you can talk here about.
All right, let's see if there's QuickBench, right? QuickBench is the site.
QuickBench, okay, this one which is on Compile Explorer also.
So I think, so there's one question which doesn't have anything to do with parallelism or concurrency. Someone asked, like, would they be able to learn about low latency programming techniques in your program? And I think you mentioned that you plan to have that.
Exactly. Let me just jump back to make this more clear. This is probably about one of my last mentoring programs, and this is about HPC. And I know of a lot of people which are highly active in the financial domain. You may notice that I gave a few presentations the last year there. And they helped me a little bit to identify what is for them highly valuable. And of course, low latency is one of the key points here. Because when you can make your transaction faster than your neighbor, you have a benefit. So once more, this is what I will address here.
Okay, yeah, that's true. And I think there's many ways where your courses will go in the future. So I don't see any more questions which are worth covering. Thank you for your time, Rainer. It was great to have you as a guest, and we'll be probably hanging out in the lounge now if you have any more things.
I will come.